Today we will be solving problem number 39, which is combination sum. This is yet another example that another problem that can be solved using the backtracking technique. Um, just like in my last video, I have explained how backtracking works on the principle of making a choice and then basically undoing it, like backtracking from that choice and then going ahead with not making that choice. So it's basically you either choosing to do something or not choosing to do something. Um, let's go through the question real quick. Given an array of distinct integers, candidates, okay, just like in the subsets problem, we had nums array. We will have a candidates array, I guess, in this problem. And the target integer target return a list of all unique combinations of candidates where the chosen numbers sum to target. Okay, you may return the combinations in any order. Sounds pretty similar. It's just the condition is like instead of it being all the subsets, we just need to return the combinations that like whose sum equals this target. And then the same number may be chosen from the candidates an unlimited number of times. So this is the key difference. In the previous subsets problem, we were not allowed to like choose the duplicate and keep like obviously you wouldn't like sets don't have duplicate elements, right? So I could not make a subset that would have two unlimited number of times. Yeah, but in this problem I can use as many twos or threes or six or sevens as I want if that reaches target and if that's a valid combination that we need to put in our result. So as you can see in this example, we have 2, 3, 6, and 7, and then our target is 7. And for output, we have like we chose 2 twice, and then we have 3, and then we just have 7, which basically equals the target. So right off the bat, I would like to say that the major difference we will have in our DFS traversal is that whenever we make a choice, so for example, I currently have nothing, and I will either choose nothing or I will choose two, right? So when I choose nothing, then I can move on and like go ahead and ahead to find other what is it like go ahead to explore other elements. But if I choose two, then I get to stay with two, or again I can go ahead with other elements. So it's just basically the key difference is that I can just keep choosing to like I can just stay here and then keep choosing to again and again and again. So we wouldn't just like choose two and then move ahead. No, we will choose two and then we will see if we can choose it again, we can choose it again or not. So yeah, that's the key difference. I would say let's just get to the code. Okay, so we will be solving this problem in a pretty similar way as we did the subsets problem. So I would start by declaring my result array, oh, result array, and also the like current combination array, which will be holding our uh, combination that we have built so far for each iteration. So this is the current, I'm just naming it core, and then the result array. And next, I don't think we will need anything else. We would just call the DFS helper that we will write next. So we will just call the DFS helper and return the result array. And now let's get started with the helper. Here we will have a basic DFS traversal helper, and we will be passing we will have parameters candidates, which is our input array, target, and we would obviously have the index from which we start for each traversal. And then we would have both those arrays that we have declared in our solution function. in our main function. Sorry. Uh, okay, so also we can solve this problem two different ways. We can either keep getting the sum for like each at each iteration. We can keep calculating the sum, or we can just basically whenever we choose the element to like whenever we choose it to be inside our current combination, we can basically subtract that element from the target and then pass that target as an argument in our like for our next traversal. So I am going to be using the ladder approach. So whenever the target reaches zero, which is basically we have like our combination sum is target, then we will push the current combination into a result. And this is going to be one of our base cases. And I'll return. Oh, sorry, I'll return. And then let's choose the let's choose the candidate. This is our first step. And when we choose, we will push it into our current combination. And after I push the candidate into our current combination, I should remain at the same index and not increase my index because I should be able to explore the same element at the same index, like however many times I want. So I will not be incrementing the index in this DFS call. So it should simply just be the same call. Yeah. And also, uh, yeah, I think I am missing. Oh, okay. Yeah, I think I should also have another base condition. So let me first write this. I have subtracted the current element and I'm just passing the rest of the arguments normally. And I should have another base case where I have explored all the possible elements, or I have like reached target and I have actually exceeded target. So in that case, I won't be able to do anything else. So I'll just simply return. So yeah, that should be one of my other base cases. So for example, if I keep choosing two, I can at max choose two like twice, right? But if I want to keep like choose two again, and it would become okay, so I can maybe choose two thrice in this example one. And if I choose two the fourth time, it would reach eight. And then that basically means that it has exceeded our target. So yeah, it won't be, that combination won't be added to our result. So yeah, and now let's continue. Let's backtrack. Let's pop it from our current combination. And then now we can move ahead with our index and no need to subtract anything. We will pass target as it is. And that should be it. I think that's it. Yeah, let's try running it. And yeah. Oh, oops. I'm sorry. I guess I'm still in the subsets problem. Yeah, it should be candidates and not nums. Uh, yeah, I think that's it. Let's run it again. Okay, yeah, it should be good to go. I think we have done everything right. Yeah, that's all for this problem. See you for part two of combination sum. Thank you.